Okay, I think we can get started. So welcome to today's workshop. Our first speaker is Pierre Degond from CNRS and Toulouse Mathematics Institute. He's going to talk about interplay between geometry and topology in models of collective dynamics. Pierre, please.
Hello. Okay, thank you very much, Veran. Thank you to the organizers for the invitation. Let's get started. Oh, my keyboard does not anymore. What's this? Okay, well, I'll try to do it. Okay, let's get started. So the talk will be about collective dynamics. So it's something that's been discussed quite at length already in this workshop. So I will be very quick on this slide. So yeah, collective dynamics refers to systems of large number of agents. Can you see my mouse here? Hello, can you hear me?
Yes.
Okay.
Yes.
Okay. Can you see the mouse?
Yes, we can see the mouse.
Okay. So you have, so in this system you have a large number of agents. Okay, here's in this experiments, in this experiment involving pedestrians, there are not so many agents, but if you look at this streets, you see that you have quite many agents. So these agents interact locally, say, with rather simple rules, but at the large scale, they form structures that are very big compared to the scales of the interactions between the agents. So in particular, these large scale are not directly encoded in agents' behavior, and one of the questions is how one can see the emergence of these structures from the models. And for this, one of the tools is the use of coarse graining and macroscopic models. Right? So here specifically in my interest currently is in trying to explore the relations between the micro scale geometry of say the agents and the agents interactions and the shapes taken by the large scale structures. So by microscale geometry, we will see an example in this talk, but basically you can think of, say, for instance, the self-propelled particles have a direction of self-propulsion that's actually a vector on the sphere. So this is a geometric, it's a geometric structure associated with the agent, but you can think of more complex geometric structures. And one of the things that we will study today is when this geometric structure is actually a frame. So that's basically looking at the agent as rigid bodies rather than single points. Right? So that's one of the questions I'd like to explore today. And the other thing is in relation with these large-scale structure, I would be interested in the topology of these structures. So for instance, to give you an example, you have these two pictures relating to flocks of, school of fish. And you see that locally, locally, if I draw a small neighborhood of any given agent here and here, basically I have the same structure. I have a direction, and the other agents actually organize in the same direction as the say tagged agent. But if I'm looking at the large scale, at the global scale, I see that this one has the shape of a line, and this one has the shape of a torus. So the topology of these, in spite of the locally the same geometry, we have globally a different topology, right? So this is the question I would be interested in here today. And as I said, our methodology will be a dual use of the microscopic models and the macroscopic model. Basically, our interest, our main focus is the microscopic model, because in somehow it's the best, is the closest, the closest model to the reality. But in fact, the macroscopic model will be used to get information on this macroscopic model, which is often very, it's often very difficult to get information directly on the macroscopic model. Right? So that's basically the topic today. So here I will be interested in, as I said, in body attitude alignment. So it's basically considering the agents as rigid bodies, trying to align not only a single vector, like in alignment dynamics, like in the Vicek model, but trying to align the full frame attached to their body. So typically in this situation, the two agents are aligned in the Vicek sense, in the sense of alignment of their velocity direction, but they are not aligned in terms of their frames. Let me give you examples of the typical outcomes of such models. So in the Vicek model, you try to align. So this movie was realized by Amic Frouvelle. So basically, in this model, you have particles that try to align with their neighbors, but there is some noise, so this alignment is sort of impaired by some noise. And so according to the intensity of the noise, what you see is quite different. And in fact, there's a phase transitions. So on the left, you have a rather large noise case, and on the right, you have a low noise case. So you see in the low noise case, you have formation of clusters of directed particles, right? So you have a symmetric braking and particles moving in a single direction. In fact, I should say that the difference in noise intensity between the two examples is very small. So in fact, there is a very abrupt phase transitions when you crank up the noise. In the body attitude dynamics, that movie was the simulation was realized by Antoine Diez using GPUs. So here you don't have so many particles, but you can actually, using this code, you can, and we'll see, actually put millions of particles. As you see, the situation is rather similar to the Vicek model, except that here you have colors encoding the body attitude. So basically, agents of the same color means that their attitude is aligned. They have basically but different colors mean different body attitudes. So you see, you have clusters forming, but these clusters have also similar body attitude, and then eventually, in this case, you have the formation of a single flock with homogeneous color. But we will see that there are many other different patterns that can emerge in this model. So, right, this is the examples that I would be interested in. I would be mostly interested in this body attitude model. So a little bit of background of this body attitude, why at all being interested in this. So there are several reasons. So in fact, if you stick to 3D, then it's actually quite interesting model for bird or fish dynamics. Actually, I mean, similar, not exactly the same, but similar model was used by Hemmerich, who's a biologist for birds. You can also actually think of something different, like pneumatic liquid crystal, but in which the molecules wouldn't be just rods, but they would be complex shape objects, and then the alignment would require the alignment of the full body of the different molecules. One example of such complex shape objects is sperm. So typically, if you're looking at a sperm cell, you see that there is it's not really a point particle, and it actually has no real symmetry. And in fact, the thing that we would like to be able to model is this, which is an experiment where you have a drop of sperm, ram sperm, which is observed under a microscope, and you see that the motion of the sperm cell induces these whirlpools, in some sense, these turbulence in the fluid. Right. So, well, actually, we will be interested in this case in multi-D, not only 3D, but many dimensions. And so this is, it can be strange to think that it can be interested in collective dynamics. After all, birds are not flying in 4 dimensions. But in fact, it can be used, and as we were seeing yesterday, some talks about that, these kinds of models can be used in data science, actually, to have data flowing, and in order to say, for instance, some shape matching or things like that. And so many data are actually structures and n-dimensional rotations, like, for instance, in the talk of Sangilha yesterday. So it is interesting, actually, to look at this model in a dimension. Also in physics, actually, it shouldn't be seen as useless to look at multi-dimensions. There are actually several trends in physics that actually infer results in 3 dimensions by using many dimensions. For instance, there is a recent progress in the physics of glasses, of ideal glasses. I'm not speaking of spin glasses, but actually glasses, which have been using actually a limit of the number of dimensions going to infinity. And from these results, actually giving results which are absolutely relevant for dimension 3. So you see that one shouldn't be sort of limited to dimension 3, even if you're looking at physics problems. There's not only this example of the physics of glasses. There are other examples I've seen in the literature recently. Right, so so far so good for the motivation. So let me go into the details of the math. So it started with a series of work which involved Amic Frouvelle, Ariane Trescas, and Sarah Merino, whom you've seen chairing the session yesterday, in these 2 works that appeared in 2017 and 2018, which were basically specific to dimension 3. But here we are going to actually provide a model in any dimension. So we have a collection of particles whose position is xk times t. Xk is, as I said, a vector in Rn, and the frame. So if you think of this girl as being a particle, it has an attached frame. So this frame is the direction of self-propulsion, and then you have 2 other frames attached to its body. Actually, to parameterize a frame, the only way I see, maybe there are others, but the only way I see is to actually define the reference frame and look at the rotation, the unique rotation that maps this reference frame to this local body frame. So here there is a little bit difference in notations. I will call, so to forget about the Q, the E1, E2, and En is the reference frame, and the subject body frame is the image of these reference vectors by the rotation AK. So for the first vector, the AK of TE1, is going to be the self-propulsion direction. So it will be so in this frame, there will be a preferred vector, the first one, which will be the direction of self-propulsion. So now what is the dynamics of the subject? The subject is going to undergo, in this example, you can actually think of different rules, but in this one, we are going to use a jump process, which is also called a piecewise deterministic Markov process, in which we have jump times for each particle k is subject to jump times tnk. So n, okay, sorry for the confusion, is not the dimension, but no, is the index of the jump time. So and the intervals between jump times are exponentially distributed with parameter nu. So in between 2 jumps, the particles just move in straight line along with the velocity defined by the direction of self-propulsion, ak of T1, with possibly a speed C0, which is the same for all particles and is constant. And very soon I will make C0 equals 1. And in the meantime, the body attitude, so the frame will not change. So that means that the time derivative of the rotation matrix AK attached to the agent is 0. And now the jump times, what's happening is that the frame attached to the individual abruptly changed. Okay, so you can think of it as not very realistic, because in practice you have more like a sort of a smooth transition, a smooth motion of it. But this this is a simplification that actually allows you much simpler computations. All right, so we're aware that this is not exactly what we like to do, but it's good enough for what we want to do, right? So now the jump times, the position doesn't jump, but the frame or the rotation matrix jumps from AK to AK prime. And let me give you how these jump occurs, right? So the first one, and this rule will be very similar for those who know to the rule in the Vicek model, but adapted to this context. So the first thing is that we compute. So we're looking at a small neighborhood of radius r to the given agent k, xk. And so for all particles in this small neighborhood, we're going to add the corresponding rotation matrices, right? Actually, we do a kind of average. And that gives you what I would call a body orientation flux, JK. But of course, this matrix isn't the rotation matrix. So we need to normalize it to restore a rotation. And for this, we use the polar decomposition, which means that if the JK is not singular, then you can write it as a product of a symmetric matrix SK and a rotation matrix theta K, right? And actually, you can write theta K as a solution of this maximization problem, right? So it's basically the closest matrix in the sense of this inner product to JK, which lies in the rotation group, right? And this dot product refers to just the traditional Frobenius inner product of matrices, right? So this thing, which is attached to the particle K, is going to be the local mean body orientation of the particle's neighbor to K, right? So if I'm looking at a sort of a picture, this is the, I'm looking only at the frames attached to the particles in the neighborhood of K. So all these points, the green, red, and blue points refer to the ends of the unit vectors of the frame. I mean 3D here, obviously, to make a drawing of the particles neighboring to K, right? So I have many of these points which make frames, and in some sense, the theta K is kind of an average of these points. So this is a thick arrow, right? So once I have this average body frame, I could say, okay, let me assume that my agent K rotates and takes the same frame as that indicated by this rotation theta K. It's not exactly what it does because there is some noise, right? So there is a noise, there is a distribution, a probability distribution, which is written like so. So if I'm given the local mean body orientation, I define a probability distribution, which is the normalization of this function e to the kappa theta dot a. Again, the dot is this inner product here. Right, and kappa is a parameter which is going to be fixed here, which essentially tells you how much noise you put in there. So actually, the intensity of the noise is the inverse of kappa. Okay, so you could think of kappa as an inverse temperature. Here is I have drawn the von Mises in dimension 2. So in dimension 2, basically, it's a vector. The frame is a vector. You need only one vector to say where the frame is. And so the origin here is basically where the big theta is. And now if you look at the distribution, you see that it has a sort of a bell shape around this theta, right? And so as kappa increases, then the shape becomes more and more narrow, right? So less and less noise, right? And what I do is I choose AK prime, the new frame, as just a sample, a random sampling of this distribution, right? So instead of taking theta exactly, theta K, I'm taking something around theta K. So here is what I do. So basically I've plotted here in these small dots, kind of the distribution and theta of A prime. And I pick up one of these frames at random around the mean body orientation, right? So if I'm summarizing the interaction process, when I'm making a jump, I have the old frame, right? I'm computing. So here this is the neighborhood of my particle. I have the frames attached to the neighboring particles. I compute the average of these frames. This is the thick arrows, and then from that I sample a new frame according to this distribution, and gives me the new frame, which will be adopted by the particle after the interaction. Right, so this is the rule, and in fact, the simulation that I've shown at the beginning is actually just a simulation of this process. Right, so it's as such, this doesn't tell us much about the qualitative properties of this model, and to understand better what's happening, I'm going to write a macroscopic model derived from this model. And writing a macroscopic model usually starts by writing a mean field model in the limit n to infinity. So in this limit, so if I take the empirical distribution of the particles, and I can show, at least maybe in simplified case compared to this one, and that has been done by Antoine Diez, that it converges to a mean field model, which is describing the distribution function of a probability distribution of particles having position x and, say, rotation a or frame a at time t, right? And so it satisfies this kinetic equation, as it's actually quite natural. You have the left-hand side, which tells you that particles move with a self-propulsion speed corresponding to the first vector of their frame, which is the first reference vector mapped by the rotation a. A is the current variable I'm considering, so f depends on a here, right? So it's a variable of f. And on the right, I have the collision process, which with intensity nu turns f into a von Mises distribution, right? Because I sample the particles according to this von Mises distribution, so it's natural I find it here. So rho f is the local density of the particles, which is just the integral of f with respect to the rotation a. And m theta f is the von Mises distribution. So that m theta here that I've written here, the e to the kappa theta dot a, with a theta f, which is computed in the same way as before. So, but it's essentially replacing sums by integrals. So I first compute the body orientation flux, which is the integral of f against a prime, dA prime. So this gives me a matrix, and from this matrix, using the polar decomposition, I form a rotation matrix theta f, which feeds into here. So basically, the process of going from f to m is exactly the same as before. So if I'm describing the distribution f as this cloud of points, right? I'm first computing the average of these frames, and this is a thick frame. And once you have the average of these frames, I sample, I construct the von Mises, and I describe the von Mises here by this cloud of points here, right? And they say the width of this cloud of points is related to the concentration parameter kappa that appeared in this formula here. Right, so essentially we have a similar model. I would need to tell you what's the measure I'm using to integrate over the group. It's actually the harm measure, which is, in this case of a compact group, the unique normalized measure, which is the left and right invariant by transposition and group inversion, right? So the reason why you need the harm measure is actually lying in the construction of the model itself, right? Because here you see that, in fact, everything is independent from the choice of the original reference frame. So if I chose a different reference frame, that would amount to multiply all the rotation matrix to the right by a given rotation. And I have to find that everything here goes through by would come up after multiplying by a given rotation or to the right as multiplied by the same rotation to the right. So you have, in particular, this sum here, which is the integral, which transfers into the integral, must be right invariant by multiplication by rotation. So naturally, the harm measure comes into the game here. So once I have the mean field model, I can rescale to get to the macroscopic scale. In here, the rescaling amounts only to assume that the interactions occur very frequently. So you just take mu as 1 over epsilon, and epsilon become very, very small. So essentially, you end up with this perturbation problem where you'd like to compute the limit as epsilon goes to 0 of this problem. And that will give us the hydrodynamic equations. Okay, so I'm going to now derive for you this hydrodynamic model in dimension n. That's a recent work that I did with Antoine and Amic, but it was previously done in dimension 3 with Amic and Sarah and Ariane. However, there are significant difficulties that appear when you go from dimension 3 to dimension n. And the reason is that in dimension 3, you have many structure that disappear in dimension n. For instance, in this paper, we use the cross product, which obviously doesn't exist in dimension n. In this paper, we use the representation of the rotations by quaternions, which also doesn't have an equivalent in dimension n. So the dimension n is more involved, I would say, than dimension 3. And this is what I want to say in this section. So the result is that if you're looking at the solution of this perturbation, so this perturbed kinetic equation, it converges to a von Mises distribution, rho m theta, where rho and theta depend on x and t, right? So rho is the local density, and theta is going to be the sort of average of body frame so in some sense, if you again, I plot here the distribution of m theta at a given location, so you can think of theta as representing the center of the distribution, and actually there is a distribution of frames that are centered around this distribution. So basically, I'm actually, once I know what is the center of this distribution, I will know the distribution. So I need to know what are rho and theta. And the answer is that they satisfy this set of equations. So the first equation is really very classical. It's the continuity equation. So here the notations are that looking at the image of the reference frame EK by theta, and I call that omega k or omega j. So these omega 1, omega n is really this mean body frame, okay? And what you can see here is that the fluid velocity, as a fluid, the particles move in the direction of the omega 1. So they move in the direction of the averages of the self-propulsion directions of the particles, which is quite natural, but there is a weight in front, which is the C1, which is less than 1. It's an order parameter that tell you if there is a dispersion of direction of self-propulsion, then the velocity in that direction in average will be smaller than 1. And it will be even smaller if the noise is large, right? So that's what's the significance of this. But apart from that, there is not much to say about these continuity equations, rather classical. The equation for theta, though, is a little bit more unusual, right? So first of all, what is this capital DT? So capital DT is a material or convective derivative in the direction of the self-propulsion direction omega 1. Weighted by the coefficients, which actually surprisingly is not the same as C1. So there is a difference between the way theta is convected and the way the density is convected. So there is a mismatch between the two convection speeds, which is actually something that's already observed in models of traffic, for instance. So it's not very surprising, right? So well, this equation says that if you move along with the particles with the speed C2, then the rotation of the body frame evolves according to the time derivative is equal to W theta. So W is an anti-symmetric matrix. So this equation is no surprise. It's actually reminiscent of rigid body dynamics. So in rigid body dynamics, you have basically everything is encoded into the angular velocity vector, and any point in the solid body, its velocity is actually computed by a vector product by the angular velocity and the distance to the center of mass, right? So there is this vector product, but the vector product generates an antisymmetric matrix. So if you write rigid body dynamics in terms of matrices, you have exactly the same structure of a time derivative of the frame is antisymmetric matrix times this frame itself, right? So this equation, the structure of this equation is nothing but rigid body dynamics. So now I have to tell you what is this antisymmetric matrix. In some sense, if I pursue the analogy with 3D, what would be the angular velocity, right? So this angular, this antisymmetric matrix has two parts. One is a first part, which is of the form F wedge omega 1. So F wedge omega 1 is just an antisymmetric matrix, which is written like this in terms of components, right? So what is it? It is a matrix, it's a rotation that, so F, what is F? F is a force vector. Let's say, what can be the force coming from? The force usually comes from gradients of the quantities. Here I have two quantities, the density. So the gradient of the density is just the pressure gradient. So there is a first component of the force which stems from the pressure gradient. But the other side unknown is the rotation itself. And so there is another component of the force which stems from gradients of the matrix theta, so which we will call body attitude gradient. So we have a pressure gradient and the body attitude gradient, and they both combine into a single force vector, right? So now this force vector enters the antisymmetric matrix into this wedge product, which describes a rotation in the plane of F omega 1. And in everything that's orthogonal to the plane F omega 1, this rotation doesn't do anything, right? And that rotation in the plane F omega 1 just tends to align the vector F, or to align omega 1 with F, right? So basically, this term tells you that the particles will tend to escape the regions of large gradients, which is what the pressure force does. And it's also going to escape the regions of large body attitude gradient, which is very natural, right? So that's, now there is another term, which is another antisymmetric matrix, which has a certain expression, but the main feature of this matrix is that it fixes omega 1. So somehow it's an inner rotation of the frame about the self-propulsion direction. It's like if the bird was, flipping its wings while going in the same direction, right? So now its expression is actually given here. So basically what this means is that I'm looking at the expression of the matrix in the basis omega I, omega 1, omega 2, omega 1. So these guys are just the expressions of the matrix in this basis omega. And you see that the entry ij is this complicated expression. It's just a trilinear antisymmetric expression involving omega 1, omega I, omega j, right? So it's basically giving you the angular velocity in the plane omega I, omega j, and it's computed by this rather clumsy expression, but it's actually just a one expression, and then you take a circular permutation of these. In particular, it's antisymmetric if you flip I and j, which it should, because it should be antisymmetric. Anyway, this is the structure. So you have a force that tends to make the particle escape the regions of strong gradients and strong body attitude gradient, and a self-rotation about the self-propulsion axis. Right, how we derive this equation, I'd like to give a few words about it, because it's actually mathematically a little bit, I think it's interesting. So you can write the kinetic equation in two parts. So the left-hand side is the transport part, and the right-hand side is the collision part. And you see the epsilon is here, so that when epsilon goes to 0, obviously you should lie in the zeros of Q. And if you look at the zeros of Q, Q is here, so the zeros of Q will be just the functions that are proportional to rho and theta, right? So any guy of this form is in equilibrium. And now you need to determine which is rho and theta. So one thing that you can do is integrate this equation with respect to A, with respect to the rotation, and that cancels the right-hand side. because by structure, the M is a probability distribution. So you see that when you integrate F with respect to A, you get rho F, and this difference gives you 0. So you should get that the left-hand side integrated with respect to A is 0 as well. And when you let epsilon go to 0, you get this equation for the transport operator applied to rho and theta dA equals 0. And if you compute what this gives you the continuity equation. So it's a very classical computation, nothing surprising here. The equation for theta is a little bit more involved. In fact, the first glance, you would like to multiply the equation by A, integrate with respect to A. But that doesn't work. The quantity that you need to integrate with is this more complex quantity, A theta F transpose minus theta F A transpose. Theta F is the rotation matrix constructed from F, right? So basically by taking the polar decomposition of JF. And you see that this matrix is anti-symmetric. And why is it the right object? Is because the tangent space to the rotation group, the Lie algebra of the tangent rotation group, is the space of anti-symmetric matrices. So you need to take someone which somehow is in this Lie algebra, and this is why you need this object. And then you do the same thing as here, and then you get that the integral of the transport of rho and theta against this object is equal to 0, which gives you the equation for theta. However, the equation for theta is a little bit not completely evident from here. Right, so let's try to see how we can get an equation for theta from there. So you do a little bit of algebra and you get this expression, which is nothing really enlightening, except that it's a linear combination of derivative of rho and theta, whose coefficients are of the form of an integral of the von Mises about the identity of A times the polynomial of A, right? And so what I need to compute is expressions like this. Right. So I can give you an example. One of the terms which correspond to the degree 3 polynomial involve this essentially computing this symmetric bilinear map. I take two anti-symmetric matrices P and Q, and I form this quantity, which is the integral of A dot P, A dot Q, A plus A transpose M identity of A dA. And this is a symmetric matrix. So you have a bilinear map which goes from anti-symmetric matrices times anti-symmetric matrices to symmetric matrices. And essentially, you need to compute the coefficients of this bilinear map. It's a bilinear map between finite dimensional spaces. So in principle, there is only a finite number of coefficients. But if you count them, there are many of them, right? Because this is dimension nn minus 1 over 2. You have to square it. And this is dimension nn plus 1 over 2. So many dimensions. And in fact, the remarkable result is that, in fact, in spite of that, this bilinear form depends only on two coefficients, real coefficients. And you can express it as the two coefficients C and C primes times these bilinear expressions here. And how you can reduce this large number of coefficients to this small number is by using invariance, of course, by the group action of SON. You can actually show that if you conjugate these anti-symmetric matrices P and Q by an element of the rotation group, and you apply B, then you get the conjugation of the result, right? And so this is basically the trick that we need to use for reducing the bilinear form. So I'm not going to give you a very lot of details. It uses actually irreducible representation of SON. In a nutshell, you can define the linear map from this bilinear map from the symmetric tensor product of anti-symmetric matrices into the symmetric matrices. And basically, the thing boils down to decomposing this thing here, which is a SON representation, into irreducible representations. And to looking at, and you also do the same for the right-hand side. And so S0n are the trace-free symmetric matrices. R is basically the scalar matrices. I have two other representations here, which I'm not going to detail. This one is the fully anti-symmetric for rank tensors. And this one is a little bit more complicated. The important thing is that if you're looking at those which are from the left and the right, isomorphic, there is only two possibilities. You either map S0n to S0n or R to R. The other representations are not isomorphic. So by Schur's lemma, it tells you that the block of the map B tilde that sends, say, this part lambda 4 to any of these must be 0, right? So this is basically using invariance, a little bit like using anti-symmetry to say that an integral is 0, right? So the Schur's lemma is very powerful. It tells you that if you have maps between irreducible representation, it has to be complex representation, they are either proportional to the identity if the representation are isomorphic, or 0. And so it's in this way that you can actually prove that this Merino map B can be expressed only by these two coefficients. Right, so this is basically a hint of the proof. And now I'm going to try to use the model to actually infer some properties of the particle model, right? And now comes the topology. Before it was the geometry, now it's the topology. And it's about topological states. And this is joint work with Antoine Diez again, and from a master's student from Imperial College. And it's a work that's going to appear in SciAm Applied Dynamical Systems. Right, so what's topological states? Topological states actually started to appear some time ago when people investigated the quantum Hall effect. And then they became very popular because there is a class of materials which is called topological insulators that, again, rely on the existence of topological states. And there are very promising materials for quantum technologies. So this is why people are very excited about that. In collective dynamics, people have started to wonder whether you could achieve topological states with collective dynamics. And there is a series of work by physicists, and now let me try to describe you this one. So basically, they're trying to see people. So this is basically Vic-Check dynamics. The particles are aligning with each other, and they are spinning in some annuli, and there are several annuli that are connected, and they have to spin different directions in order for the rotations not being frustrated, right? So you have this elementary pattern where you have two annuli where particles flow to the left and one where they flow to the right, and then you paste all these patterns together in the form of a lattice. And what's happening is that then you have this flow flowing here in this, and then you perturb the flow on the side by, let me give you a video taken from this paper. Here is so you have to imagine that there is, a particle flow in all these annuli, and then you perturb this flow by a small source on the side, and you see what's happening is that this perturbation propagates in one given direction around the edges of the lattice, right? So this is a typical topological state, which is called a Carroll edge state, right? This is the background flow field here. Okay, so there's been a lot of work actually trying to reproduce topological states in collective dynamics. And our goal is actually to explore such topological states with our body orientation model. And these works were mainly focused using macroscopic model, and we'll try to do that at the macroscopic level, which is more complicated because we have to sustain the noise, right? So that's and one of the motivations in life science would be actually, in my view, that topological protection. Topological protection is that the fact that these Carroll edge states are very robust because they have a non-zero topology, say non-zero winding number. So when you want to perturb them by some external phenomenon, you need some finite amount of energy. So whatever perturbation has a lower amount of energy won't perturb this Carroll edge state. So these topological states provide increasing robustness, and one of the questions is whether this topological protection could be seen in living systems, because one open question is to understand living systems robustness against the noise. Of course, I'm not pretending that our model is reproducing what's happening in some living systems. I think it's a nice sort of case study, I would say. right? It turns out that with a macroscopic model, I can actually provide a whole family of interesting topologically non-trivial solutions. So let me give you one of them, which is this one. So this is the initial state. So it's, this is the macroscopic model. So you have to imagine that I have to draw a field of frames. So at any point I have a frame. So I draw this frame at certain selected number of points. And you see that the solution is such that it's invariant in along the coordinates x and y, but it varies along z. So that's at a given time. This is the initial state. So the red arrow is the direction of self-propulsion, right? And what you have is what you move when you move along this vertical axis, the frame spins around the self-propulsion. So the green arrow makes a circle around the red arrow, and after one period, it returns to its original position. So you have along this direction, you have a non-trivial topology. If you look at the winding number of this vector, it's 1, right? And what's happening is that when you have that, what you observe, what you can compute as an exact solution of the model is this. So the frame starts to rotate, to spin around this axis z, and you see that since the red arrow is the self-propulsion direction, the particles will actually spin in circles as well. So which is the reason of the milling terminology, right? So this is an exact solution of the macroscopic model, and now we would like to try to see if the microscopic model will actually follow this macroscopic simulation. So here in this case, I have pasted 2 mills, one on top of the other, so that actually the winding number is 2 instead of 1. And I'm going to show you an outcome of the simulation. So what you will see is that the particles which are coming from left to right originally are turning, and that's the milling effect, going to move towards in front of you, towards us. This is the state now. And they are turning to the left now, and next they are going to turn and going to go away from us. It's now going to show because the back of the particle is yellow, so you show it now. But after some times, because of stochasticity, you have some mess up that appears, and eventually after a messy phase, you see that all particles are floating. So you see that these topological solutions are staying for some time, but then they eventually destroy. Let us compare with a solution which has no trivial topology. So here I've pasted 2 mills, but I have reverted sort of the rotation of the second mill compared to the first one, which is seen in these 2 different sense of these arrows here. And what you will see, obviously, is not obvious actually. What you see is that the particles are spinning in different ways in the bottom and the top of the figure. Okay, it's something other seemed to happen, different from the previous one. Eventually, it looks like it's becoming a flock. So could we understand the differences of the differences between these two behaviors? And for that, we constructed an indicator that tries to measure the following. You see that in this situation, the frames are all constant on each horizontal slide, right? But when you move from one slice, but when you move from one slice to the next, then they change. So on a given slice, if you look at this green vector, it makes an angle with the horizontal axis. And this angle changes. We call that the roll angle. And we are going to actually measure the average roll angle in all the slices. That's one of the things that we are going to do. We are going also to measure the amount of noise, because in the particle case, not all frames will be exactly aligned. So to measure how much disalignment there is, we are going to construct a vector, a vector who is going to be directed along the direction of the green vector, but whose norm would be smaller if there is more noise. So if there is no noise at all, the vector will be of unit norm. And if there is more and more noise, then the size of the vector will decrease. Okay, so this is how we're going to measure what's happening. The construction is explained here, but I'm going to skip it because it's not difficult, but it's a bit complicated to explain. And I'm going to show you, first of all, let me stop now here. So here, what I put this vector. So for instance, if I'm looking at the slice, which is at, say, height 200, which is mostly yellow, right? So I'm looking at the point which is here. And you see that at this slice, the green arrow, the green arrow of the frame is pointing in this direction. And because the vector is not exactly of unit norm, there is a small amount of noise. Obviously, in the slice which corresponds to 700, it points in the same direction, but the amount of noise is much bigger, right? And you see, because we had two mills, two periods from the bottom to the top slice, we have two circles. We have a circle that spins twice around the origin. So by looking at this curve, we are looking at basically the direction and noise in each slice, right? So now I'm looking at, back to this, I'm looking at the milling solution, right? The milling solution, originally I had two mills, running number is 2, so I have almost perfect alignment. So the vector is almost of norm 1, and it spins twice around the origin, right? As I move from the bottom slice to the top slice. And then I go on, and you see that when I'm, for a certain time, the structure remains the same. And that's the time where things follow the macroscopic model. And after some time, noise starts to increase, and which means that the curve gets closer to the origin. Noise starts to increase, but the structure remains. So that means you have still two mills, you have still a topologically non-trivial solution. And then catastrophe happens. You have the curve that crosses the origin. When you're near the origin, that means that you have only noise. You don't have any alignment anymore. So what it means is that you have a phase where you have complete disorder. And then after the phase of complete disorder, everything reorganizes into a single flock, which is a single point. So here again, order has emerged again, but a different kind of order with trivial topology. So you see that what this illustrates is that if I have a topological transition, getting from winding number 2 to winding number 0, I need to go through a phase of total disorder. And to compare, I'm going to show you what happens if I get the topologically trivial solution originally. So the two mills that are pasted one in the other sense as the other. What's happening is that you still have you just have an opening of this curve, but you see that the amount of noise is absolutely 0. It stays completely coherent, right? It's just a standard, relaxation. You keep the solution, but you just relax to a single flock. So you see that there is no topological transition, so there is no need to go through this state of full disorder, right? So this is a way actually we could characterize these topological phase transitions. Right, so this is only the beginning of the story of these topological phase transition. I'm just going to wrap up now. And so, okay, this is the summary. This perspective, I think, is that, okay, mathematically, actually, there is a lot of things to say about these models, in particular the hydrodynamic model. We were able to prove that it's hyperbolic, so at least it's a hint that it has a good behavior. But there are a lot of things to say about numerical simulations and so on. But in terms of geometry and topology, I think that this is only an example of what you can get with a non-trivial geometrical structure at the particle level, and we would like to investigate more examples and maybe try to give a unified theory for these complex geometrical objects. And we would like also to analyze topological states in more detail with some more phenomenal studies, and also to look at other classes of topological invariants rather than just the impacts of a vector. So on this, I'm going to finish and thank you for your attention.
Okay, thank you very much for a nice talk. We have time for questions. I will start with a simple one about the modeling. So when you were modeling using a frame, somehow the slides was off. Pierre, can you hear me?
Yeah. You want me to share the screen again?
I think so. Yeah, just for questions.
So you want to see the
Oh, I just have a quick question about the modeling. So between the two jumps, I see that the direction of the birds, say, is along the first component of the frame.
So the direction jumps, but also the body attitude.
Right, but what about the speed? Like, why the speed is given?
The speed is always constant.
The speed is always constant.
It's just an invariant. It's in fact it's in one in the macroscopic model after rescaling. Yeah, it's a Vic-like model. In the Vic model, you have constant speeds. So this is a way to model self-propulsion. You model self-propulsion, saying that whatever happens to your agents, they move with speed 1.
Okay.
It's a simplification, but I think that it's actually the difference with the Cooper-Smale model, where you adjust the speeds as well. But it turns out that the mathematicians like the Cooper-Smale model more, but the physicists like the Vic model more, because it has less parameters. So the Vic model was seen as a kind of a minimal model because it has only very, very, very few parameters. And it can be shown that you can relate one to the other by some singular limit. I think Jose has worked on that. So there is a connection between the two, but as you're taking a singular limit, sometimes limits do not commute, as you know, and so some of the things that you can prove on the Cooper-Smale model, that's actually wrong for the Vic and vice versa. And so this is why I think that the study of the inner geometrical structure provided by this constraint, that the velocity is 1 in the Vic model or by the frame, is interesting. Actually, it turns out that for the body orientation model, you can't actually find this model as a relaxation of an unconstrained model. So you can think of a matrix model. You could think of a matrix model and say, okay, I put a relaxation to rotations, but actually you don't find, it doesn't commute. So you will not find the same hydrodynamic model.
Okay, I see. Thank you. Other questions? Okay. One second.
Hi, thanks for the great talk.
Maybe
I missed this, but what did you do with big R, the radius of the ball?
Yeah, I slipped it under the rug. Yes, when I do this, I've taken the limit of R to 0. In fact, here I should have. If you take the direct mean field limit of this model, you would have a double integral here, and the other integral would be an integral in space over a small ball centered at x with radius r. But actually, when doing the hydrodynamic rescaling, one possibility, I'm not saying that you should do that always, but what we've done is actually to tie R to epsilon, to say that R is of order epsilon, right? So in the limit, you get with local integrations, right? But you could make other choices, obviously. But this is a reasonable one in the sense that at large scale, the radius of interactions of the particles is usually very small.
Okay. Is there any other questions? One more, if there is any. Okay. If not, then let's thank Pierre again for a nice talk.